Hello class, today I'm going to be going over your test 1 review. So this is your test 1 review. And if you go into Blackboard under week 2, you'll basically find your test 1 review. And if you pull up that Word document, I'm basically just going to be going through each one of those multiple choice questions. It's about 52 questions. I know it seems like a lot, but some of them are easier than others. Some require more thought, some you can get through pretty easily. But I'm just going to go through each one of those just to make sure that each one of those answers makes sense. So let's dive right into it. So the very first question says, the scientists first accredited for discovering the concept of inertia. So the scientists accredited for the concept of inertia was, let's see, Copernicus, Aristotle, Newton, Galileo. Well, Copernicus basically studied the planets. He was the one that first came up with the idea that the Earth is revolving around the sun and not the sun revolving around the Earth. So Copernicus came up with the heliocentric viewpoint, which basically means revolving around the sun. Aristotle was the father of logic, as we kind of know. Newton came up with the laws of motion, and Galileo was the one that came up with the concept of inertia. So this one's going to be Galileo. Number 2 says, Galileo said that if you rolled a ball along a level surface, it would. So if you rolled a ball on this level surface here, because of inertia, if this were a frictionless surface, this ball will continue to roll on forever until acted on by some outside force. So because of inertia, this ball is going to continue to roll. And that's going to be, let's see, it looks like it's going to be number D, or letter D. So the ball will keep rolling without slowing down if no friction is acted upon it, right? And so Galileo did another experiment where he rolled a ball down an incline and up another incline. Right. So when Galileo did this experiment, he noticed that if the ball started up here, it would basically roll up to that same level. So that's number 3. It says when a ball rolled down an incline and up another, he found that the ball rolled nearly to basically its initial height. So this is the initial height, and then it's going to roll down and go back up to, its same initial height that it was before. So that one's going to be A. See, number 4 says a probe in space continues its motion due to, let's see, so A, it's seeking a continued state of motion, very low friction, its own inertia, or none of the above. Let's see. So for that one, for something to, well, basically, A and C kind of say the same thing, but the correct answer is actually C. All right, so the correct answer is actually going to be C. For a space probe to continue, its motion around the Earth, basically what's keeping it in that motion is its inertia. And then also gravity, so like here's Earth, there's a space probe, and it's going around in this direction. And so we know basically the gravity from Earth is attracting that probe basically towards it, causing it to kind of fall around it. But it's the probe's inertia that also keeps it in that motion as well, similar to the ball rolling on a frictionless plane. So for number 4, that's going to be C. Number 5, a kilogram. A kilogram is basically a measure of mass. I think that's pretty easy. So if something is 10 kilograms, that basically describes its mass. Compared to a 1 kilogram block of solid iron, a 2 kilogram solid block of iron has twice as much what? So we have, say, a 1 kilogram here and a 2 kilogram here. So we know since this one has more mass, it has more inertia, about twice as much inertia because the mass is twice as much. So A would be right. It has twice the volume because they're made out of the same material. And so since it has twice the mass, it also has twice the volume. And obviously it has twice the mass because it's 1 kilogram. That's 2 kilograms. So for 6, it's going to be all of the above. So for 7, it says a ball weighs 1.5 newtons on Earth. So let's see, a ball weighs 1.5 newtons on Earth. And another type of ball weighs 1.5 newtons on the moon. And then they ask, the ball with the greater mass is which one? So let's say we know the force of gravity on the Earth and the moon. For the Earth, the force of gravity is roughly about 10. And for the moon, the force of gravity is, I don't know it off the top of my head, but it's way less. Let's say it's about 1. I don't think it's actually 1, but we know it's smaller than the gravity of Earth, right? Because if you go to the moon, you can jump higher and kind of, you'll feel less, or you'll feel that you weigh less because the gravity is less on the moon. So let's just say it's 1. So now that we know the gravity on the Earth and the moon, and we know the force that's being pulled down, we can actually find out the masses for both of these objects. So on Earth, if we know the force of gravity is given by mass times g, which is the gravitational acceleration, we can solve for what the mass is. So let's erase this. So basically the mass is going to be the force, which is 1.5 newtons divided by g. So the force divided by g. So sorry if you can't see that, it's supposed to be a force of g, Fg. So for Earth, that's going to be 1.5 divided by 10. And so that is 0.15 kilograms for Earth. For the moon, if you were to do that same thing, it would be 1.5 divided by 1, which is basically still 1.5 kilograms. So the object that's on the moon that's 1.5 newtons weighs more than an object on Earth that weighs 1.5 newtons. That makes sense, right? Because for it to be pulled down or have the same weight on the moon, this object must have more mass. So the answer to this one is going to be number 7. It's going to be B, the other type of ball. The other type of ball that's basically on the moon. Number 8, the net force on an object is the combination of all the forces acting on it, right? So basically, if you have multiple forces acting on an object, the net force would be just the sum of all those forces. So net force basically equals a sum of all forces. And so let's see, then that goes right into number 9. It says a girl pushes a cart to the left with 100 newtons of force. So let's say this is our cart here, being pushed this way to the left with 100 newtons of force. At the same time, a boy pushes it to the right. So it's a boy pushing it this way. And he pushes it with the force of 50 newtons. And so the net force, which is what the question is asking, what is the net force exerted on this cart? The net force is going to be the sum of those two forces. So the sum of the forces. it's going to be equal to, well, since these forces are pointing in opposite directions, they're basically going to be subtracted. And so let's say I say to the right is positive and to the left is negative. And so this would be 50, basically minus 100. And so that would give us negative 50 newtons, where here the negative just means it's being basically pulled towards the left or pushed towards the left because the girl is pushing it with more force. So that's what that negative means. So the answer is going to be 50 newtons towards the left, which is D for number 9. All right, so the next one, number 10, says an object is pulled with 3 forces now. Let me write it out. An object is pulled with 3 forces. So let's say we got our object here. It's being pulled with 3 forces. One is 20 newtons to the right. So this force of 20 newtons. Force of 20 newtons. And another force of 40 newtons to the right. So boom. Newtons, and a third force of 30 newtons to the left. Boom. And so now they're asking what the net force is, where again, the net force is just the sum of these forces. So let's do that. The sum of the force is going to be, well, it's going to be this force plus that force minus this force, because that one's going in a different direction. So it's going to be 40 plus 20 minus 30. That's going to give us, well, that's 60. 60 minus 30 is 30. So it's going to be 30 newtons. And notice it's positive, so that means it's going to be 30 newtons to the right. And so for this one, the answer is going to be, let's see. So it looks like it's actually going to be none of the above, because they do not give this answer in the options. They do give 30 newtons to the left, but we know it's going to be 30 newtons to the right. So for number 10, I believe it's going to be none of the above. Let's check the bottom. Yeah. So number 10 is D, none of the above. And make sure you kind of keep up with which direction the net force is going to, pull, because you very easily could have chosen 30 newtons to the left, and that would have been wrong. So number 11 says, which has 0 acceleration? So 0 acceleration, so the acceleration equal to 0. A, an object moving at constant speed. B, an object in mechanical equilibrium. C, an object at rest. Or D, all of the above. Well, if an object is in constant velocity, so constant velocity indicates that the acceleration is 0. And if something is in equilibrium, that indicates the acceleration is 0. And if something is at rest, that also indicates the acceleration is 0. So basically all 3 of those answers are right. So for number 11, that's going to be D, all of the above. Let's see, 12, the force of friction on a sliding object is 50 newtons. The applied force needed to maintain constant velocity is, so we've got some object here. It's on some surface. This surface has friction on it. And let's say you push it. You push it that way. But since you're pushing it that way, we know basically friction is going to push the other way. So this is what I'm calling friction, and friction is 50 newtons, the force of friction. So basically, how fast or how hard or what force do you have to push this box that way in order for it to maintain a constant velocity, well, we know when the velocity is constant, if the velocity is constant, constant velocity basically means the acceleration is 0. So in order for the acceleration to be 0, the net forces have to cancel out. So basically, you have to push this block with 50 newtons the other way. You have to push it 50 newtons this way. And why do you have to push it 50 newtons that way? Well, if you do the sum of the forces now, which you know should be equal to 0, because it has a constant velocity, and whenever the velocity is constant, the acceleration is 0. Or you could think about it like this. We know the sum of the forces also equals mass times acceleration. And if the acceleration is 0, that makes that 0. And then so these two forces basically have to cancel each other out. So we have 50, basically 50 that way minus the other 50. And obviously 50 minus 50 is 0. So that's how we get a 0 acceleration, but it's going at a constant velocity. So all that just to say, the force that you need to apply is 50 newtons, and that looks like that's going to be B for 12. Excuse me. So now number 13. So number 13 says, what two measurements are necessary for calculating average speed? For average speed. Well, average speed is given by, I'm just give you the equation, it's given by the change in position divided by the change in time, where this triangle that I drew here basically just means the change in. The triangle means change in. And so you can also write it like this. The change in would basically be the final position minus the initial position. So the final position minus the initial position is basically the change in position divided by the basically the final time minus the initial time. So to calculate average speed, we need distance and time, where this top part is the distance and the bottom part is the time. So the answer to number 13 is going to be, looks like it's going to be D. And we just check the bottom. So 13D, yeah. So number 14 says, a glance at the speedometer on your vehicle will tell you your A, acceleration, B, average speed, C, overall speed, or D, instantaneous speed. Well, this one might be a little tricky, but well, we know for one, it's not the acceleration. Your speedometer does not tell you how fast you accelerate. It actually tells you your instantaneous speed, because as soon as you speed up, your speedometer then tells you your new speed at that exact moment. It doesn't tell you the average speed, because your average speed would be over the whole length of your travel, so to say. So like if you start over here and end up over here, you could be driving really, really fast, and then kind of slow down a little bit, and then could drive even faster, then slow down a little bit, and then drive fast towards the end. So these big arrows indicate like here you're going fast, here you're kind of slowed down, here you're going fast, slowed down, and here you're going fast. The speedometer is going to tell you how fast you're going in each one of these moments, whereas your average speed is just going to take the average over this whole distance here. So for number 14, your speedometer tells you your instantaneous speed. So it's going to be D. So number 15, in a dream, you're traveling at 50 kilometers per hour and you bump into another traveling car towards you at 58 kilometers per hour. The speed of impact. The speed of impact. So basically we have two cars going into a head-on collision where this one's going at 50, this one's going at 48. So to find the speed of impact, basically all you have to do here is just add up those two speeds. So the speed of impact is going to be 98 kilometers per hour. All right. So that would be a pretty major accident. So that looks like that's going to be number B for 15. So whenever they ask you for the speed of impact, it's always going to be the sum of the velocities, or just add them up. And notice here, just because they're going in opposite directions, we didn't actually subtract them. We actually still added them, even though they were going in opposite directions. And that's because they're asking for the speed of the impact. So let's see, number 16. Number 16 says the average speed of a horse that gallops a distance. So we're looking at average speed. Average speed, which is going to be equal to the change in that distance over the change in time, right? It said it gallops a distance of 10 kilometers in a time of 30 minutes. Well, if you notice, the answer choices are in kilometers per hour, but the time that they give you is 30 minutes. So we want to basically change the time into hours so that we can get the units to match up. So 30 minutes is basically what in hours? Well, it's basically half an hour, right? So this is the same as saying 0.5 hours. Or you could write it as half an hour. So you could write it as 0.5 or half an hour. I'm just going to write it as 0.5. So now we can just take that 0.5 hours now and put it in for our time. And the distance is going to be 10 kilometers. So it's going to be 10 kilometers divided by 0.5 hour. And now we just divide those two, and that's going to give us basically 20 kilometers per hour. And so the average speed of that horse is going to be 20 kilometers per hour, which is D for number 16. So now number 17, if a ball rolls down an inclined plane and gains 4 meters and gains a velocity of 4 meters per second each second it rolls, what is its acceleration? So if something speeds up by 4 meters per second each second, that basically means it's accelerating, right? So as each second passes, it's going 4 meters per second faster. And so basically the acceleration then is 4 meters per second squared. So you can say, at 1 second, it's moving 4 meters per second. At 2 seconds, now it's moving at 8 meters per second. At 3 seconds, then it's moving at 12 meters per second, and so on and so on. So basically the acceleration is constant while the velocity is steady increasing by 4 meters per second. All right, so what number was that? That's number 17. So number 17 is going to be A. Number 18 says a motor scooter undergoes acceleration when it decreases speed, changes direction, gains speed, or all of the above. Well, basically we know acceleration is whenever velocity changes. And so it's pretty clear, if you speed up, then your velocity is changing. If you slow down, your velocity is changing. But also, if you change direction, like if you turn around a curve, then your velocity is still also changing because you're changing direction. You know, I talked about say you're driving in a circle with driving in a circle here. So basically, as you drive around this circle, the direction of your velocity is changing. So you're accelerating as you turn, basically. So for number 18, it's going to be all of the above. Number 19 says a free-falling object has a speed of 30 meters per second at one instant. Exactly 2 seconds later, its speed will be what? Well, we know free fall. Whenever an object is in free fall, the acceleration is going to be due to gravity. It's going to be equal to 10 meters per second squared. Which basically means as each second goes on or passes, the velocity is going to increase by 10, right? So if 2 seconds pass, the velocity is going to increase by 20 meters per second. And so if it's already at 30, after 1 second, it's now moving 40 meters per second. Then after 2 seconds, or after basically another second, I'd make this after 1 more second, it's now moving 50 meters per second. So 2 seconds later, it's going to be moving at 50 meters per second. So the answer to number 19 would then be D. So number 20 says when dishes remain on a table, when you yank the tablecloth from beneath them, you are demonstrating what? Well, this is basically the inertia concept that we talked about in, I think it was the first lesson. So like if I have this paper here and I put this cup down on top of it, if I slide this paper at a fast enough speed, then the cup will tend to stay there. And that's because this cup has some inertia. What inertia is basically the resistance to change. So number 20 is going to be D. Number 21, when you step off of a moving bus, a bus moving at 2 meters per second, your horizontal speed when you meet the ground is, so if you're on this bus, I don't know, something like that, it's going this way at 2 meters per second, and instead of waiting for the bus to stop, you try to hop off really, really fast. The speed of which you contact with the ground is going to be the same speed as the bus because you were once on the bus and the bus was moving. So same way, if you ever try to, step out of a car while it's moving, you'll kind of stumble a bit because you're still moving in the same direction as that vehicle. So for number 21, the answer is going to be B, about 2 meters per second. 22 says a constant force on a railroad car produces a what? A constant velocity, a constant acceleration, both of these, or none of these? Well, if there is a constant force on an object, so the force is constant, and we know the mass is constant, then that's going to make some constant acceleration. So if you have a constant force, you have a constant acceleration. And this is basically similar to an object in free fall, where an object in free fall has a constant force of gravity pulling downwards on it, and so it accelerates downwards. So a constant force produces a constant acceleration. Acceleration. I can't see that. Whereas a constant velocity means acceleration is 0. So make sure you don't mix those two up. A constant velocity means acceleration is 0. A constant force means a constant acceleration. So for 22, the answer is going to be B. For 23, a push on a 1 kilogram brick accelerates the brick, neglecting friction to equally accelerate a 10 kilogram brick requires the force to be how much? Okay. So basically we apply some force to a 1 kilogram brick. So 1 kilogram brick. And we also apply that same force, well, not the same force, to get that same acceleration. Let's say the force you apply is 2. So the force you apply equals 2, so this is 2 newtons. The acceleration then is going to be 2 meters per second. All right, so we're trying to figure out how much force was required or needed to push a 10 kilogram mass to that same acceleration. So we're trying to find this force here. So we can solve for this force by taking this 10 and multiplying it to the other side there. So we see here the force now needed is going to be 20 newtons, whereas originally the force we used was 2 newtons. So basically you need 10 times more force to push a mass that's 10 times more massive. So all that to say is if you increase the mass by 10 times, in order to push that mass at the same acceleration, then we must apply 10 times the force. So for number 23, that's going to be C. So 24 says, Lillian pulls on a 10 kilogram wagon with a constant force of 30 newtons. What is the wagon's acceleration? Well, this one's pretty easy. We just use Newton's second law that says acceleration equals force over mass. The force is going to be, well, let's see, she pulls on it with 30 newtons divided by, 10 kilograms. So that's going to give us an acceleration of 3 meters per second squared. Boom. So that's going to be, for 24, it's going to be E. Yeah. Check the bottom. 24, it's going to be 24, this is C. 24. Oh, excuse me, 24 should be C. I looked at the wrong one. So it should be 3 meters per second squared, and that's C, not E. Okay. So number 25 says, when you throw a rock straight up, reaches the exact top of its path, its velocity is, So if we're standing here and we throw a rock upwards, we know it's gonna go up, pause at the top, and then kind of fall back down. So at the top here, we know the velocity is gonna be equal to 0. But while the rock goes through this path here, the acceleration is still constant. Acceleration is due to gravity. So that's gonna be 10 meters per second squared. Even while this rock is at the top, the acceleration is still 10 meters per second squared, but the velocity is 0 at the top. So that's gonna be A for 25. So 26 says an iron ball and a wooden ball of the same size are dropped from a tall tower. Taking air resistance into consideration, the object to hit the ground first will be, well, this problem is a little tricky because you may want to say they both hit the ground at the same time, but that would be true only if there were no air resistance involved. But since we are taking into consideration air resistance, the iron ball, since the iron ball is probably heavier and maybe more dense, and since it's more dense, basically the air won't affect it as much. So the iron ball probably falls slightly faster than a wooden ball, which is probably less dense, more porous, so more air would actually affect that wooden ball. So taking into consideration air resistance, the iron ball would hit the ground only slightly before the wooden ball. It probably wouldn't make that big of a difference, but slightly enough to where the iron ball hits the ground before the wooden ball. So yeah, just make sure you read these questions carefully when you take your test, because that's basically a trick question, one you could have easily missed if you did not read it carefully, right? So now number 27 says when you rub your hands together, you A, can push harder on one hand than the other, B, cannot push harder on one hand than the other, C, need more information. Well, this here just uses Newton's third law, right? That says every action has an equal but opposite reaction. So basically, if I push on this hand that way, then when my finger pushes on my hand that way, then my hand is also pushing on my finger the opposite way by the same amount. And so basically, the answer for 27 is going to be you cannot push harder on one hand than on the other hand because they're basically equal forces, but they're just, pushing in opposite directions. So that's going to be B for 27. Number 28 says when a baseball player hits a ball with a force of 1,000 newtons, the ball exerts a force on that bat of, well, this again uses Newton's third law, right? And so since the bat hits the ball with 1,000 newtons, the ball must also be hitting the bat with 1,000 newtons, but in the opposite direction, because every action has an equal opposite reaction. So for 28, the answer is going to be A. 29 says a player catches a ball. Consider that action force to be the ball. So consider that action force to be the ball against the player's glove. The reaction is going to be the player's grip on the glove, the force of the glove on the ball, muscular effort in the player's arm, friction on the ground against the player's shoes, or none of the above. Well, so if the ball is interacting with the glove, then the reaction force is going to be the glove interacting with the ball. So the answer for that is going to be basically B, which again uses Newton's third law. Number 30 says a Mack truck and a Mini Cooper traveling at the same speed collide head on. So we got a Mack truck and a Mini Cooper. So obviously we got this Mack truck here, you know, real big, and we got a Mini Cooper, real small. If these two cars collide head on, let's see, it says the vehicle to undergo the greatest change in velocity will be, well, it's gonna be the Mini Cooper, right? Because the Mini Cooper has a smaller mass. Even though they're gonna basically crash and, you know, hit each other with the same force but in opposite directions. So like this Mack truck is gonna crash into the Mini Cooper with a force that way, and the Mini Cooper is gonna crash into the truck with a force that way. Equal but opposite forces, but since the Mini Cooper has a smaller mass, its change in velocity or its acceleration is gonna be a lot more. So for number 30, the answer is going to be A, the Mini Cooper. 31 says, for a falling ball, the action force is the pull of the earth on the ball. All right, so that's the earth. So it says the action force is the pull of the earth on the ball. So the earth's pulling the ball downwards like this. But the earth, well, the reaction force would be the earth being pulled upwards by the ball. All right? Because for every one interaction, there's always equal opposite forces. So these forces are equal but opposite. But notice the earth is basically not going to move that much because the earth is so massive compared to this little ball. So this ball is going to move more towards the earth than the earth is going to move towards the ball. But the earth is being attracted by the ball upwards. It's just not moving because the earth has so much mass. So the reaction force is going to be the pull of the ball on the earth. And that's going to be C for 31. So now number 32 says, according to Newton, the greater the masses of interacting objects, well, sounds like to talk about Newton's law of gravitation, which you know is given by boom, isn't that right? So we know if basically the greater the masses, the greater the force between those masses. Right, so if we increase the masses, that's gonna increase the force between the two. So for number 32, the answer is gonna be A. Now for number 33, if the Earth's mass somehow decreased with no change in its radius, your weight would what? Well, we know your weight is basically related to how much force the Earth is pulling down on you with. So you can actually kind of use this same equation. Let's say M1 is for the Earth and M2 is your mass. If you decrease the mass of the Earth or decrease M, that basically is going to decrease the force between you and the Earth, right? Hence, if you decrease the mass of the Earth, then that would also decrease your weight. So for 33, the answer is going to be A. Now for 34, it says, why doesn't the moon fall towards the Earth like apples do? So here's the Earth, and let's say here's the moon right here. So they're asking, why doesn't the moon fall downwards towards the Earth like apples do? Well, the moon is actually falling downwards, but because the moon has this velocity, or this tangential velocity, with the Earth, it's actually falling around the Earth. So it is falling downwards, but because of this tangential velocity, it's falling around the Earth and not actually straight down towards it. So for 34, the answer is going to be A. The moon does fall, but due to its tangential motion, it also falls around the Earth. All right? 35 says, consider two planets in space that gravitationally attract each other. If the mass of one of the planets is doubled, the distance between them doesn't change, then the force between them is what? Well, that just goes back to this. Big G M1 M2 over D squared. If we change M1 and double it, and so now it becomes 2 M1 M2 over D squared. Well, notice basically everything is the same as in here. Boom. So if we double the mass for one of them, notice how everything else is still the same as it originally was, but now there's a 2 in the front. So basically the force is going to be doubled because of that 2 if we double the mass of one of the objects. So for number 35, the force between them is going to be twice as much, or A. And that's if we double it for one of the planets. So similarly, if we were to double the size for both of those planets, then it would be a 2 and another 2. And then the force between them would be quadrupled, because it'd be 2 times 2, and that'd give you a 4 there. So now number 36 says, according to Newton, the closer gravitationally interacting objects are to each other. So the closer two objects are to each other, so if this distance between those two objects gets less and less, then the force between them is going to basically increase, right? And that kind of goes back to the inverse square relation. So this bottom is basically the distance between two objects. So if you decrease the distance between two objects, the force here is basically going to shoot up between those two objects. So for number 36, the answer is going to be C. The more gravitational force between them, the closer two objects are to each other. 37 says, a woman who normally weighs 400 newtons stands on top of a very tall ladder. She is 1 Earth radius above the Earth's surface. What is her weight there? Okay, so we draw Earth here. Earth has some radius r, and when this woman stands on Earth, she has her weight, or her force, equal to 400 newtons. So she goes atop a tall ladder. So I just draw it like this. And we know the length of that ladder is r. And so now she's way up here on this ladder. What is her weight now that she's way up there on top of the ladder? Well, here we can again use Newton's law of gravity. D squared. So let's say we use this, for when she's at the bottom, right? When she's on the Earth. So when she's on the Earth, this is going to be equal to the 400 newtons. And then the distance is actually going to be r. So that's going to be r. And so now let me use this same equation for when she's way up here now. So now it's going to be, the force is going to be G M1, M2, where M1 and M2 is the mass of the Earth and her mass, which are both going to stay the same. But the only difference is now she's going to be 2r away because it's this r plus that r. So that's how far she is. So it's going to be 2r squared. 2r squared. All right. So if I were to square the bottom there, then that would give me G M1 M2 over, set of 4r squared now. Now notice how all of this right here is the same as that up there. So basically, all of that part is going to be equal to the 400. And so we have to take that 400 and actually divide it by this 4 here to get how much she weighs up here on top of the ladder. So 400 divided by 4 is, so her new weight at the top is going to be 400 divided by 4. It's going to be 100. So if she were to climb a ladder that is the exact same radius of the Earth, which is, a crazy, crazy big ladder, once she goes up there on top of that ladder, she's going to weigh or feel that she weighs a fourth less. She's only going to weigh 100 newtons versus her weight on the surface of the Earth being 400 newtons. So for 37, the answer is going to be A. 38 says, how far away from the Earth must one travel to completely be beyond Earth's gravity? Well, let me draw the inverse square graph here again. Right? So we know this is the inverse square graph that basically describes Newton's law of gravity here. So basically, since, this is never actually going to hit 0, it never actually hits 0, it just gets really, 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 really small. That basically means no matter how far away or how big the distance is, the force here never actually hits 0. It just gets really, really, really tiny. So that basically means you can never really go far enough to get beyond Earth's gravity, because Earth's gravity kind of, expands everywhere into space. But as you get further and further, it can get so small to that it doesn't matter, but it will never actually reach 0. So for number 38, the answer is going to be A. 39 says, an outcome of universal gravitation is A, its discovery prompted other laws of nature. B, planets are not cubes with sharp corners. And C, it provided prediction and discovery of planets. So that's actually going to be all of the above. So Newton's law of gravitation basically did a number of things in science. So, it actually connected gravity on Earth with the stars. It allowed us to discover other planets that we couldn't actually see. All those good things. So for here, the answer is going to be D, all of the above. Number 40, planets wobble in their orbits due to what? Well, planets wobble in their orbit, and a wobble basically means, so let me kind of draw this out here. Let's say here's the sun, and way out here we have two big planets. It's like Jupiter and Saturn. Let's see how I'm gonna draw that. See, Jupiter and Saturn. So we know Jupiter and Saturn are both really, really big planets. So we know basically both of these planets are both attracted or being attracted towards the sun. But since both of these planets are so massive, you could think of Saturn here. Well, this is Saturn. I'm gonna put a ring on it. Saturn is actually big enough to be pulling on Jupiter just a bit, causing it to kind of wobble this way. So kind of wobble that way. Then it's also being pulled the other way by the sun, right? So basically all that to say that the perturbation or the wobble of these outer planets or these massive planets is caused by Newton's law of gravity. All right, let me pull back up my review here. And let's see, that was number 40. So number 40 is going to be A, because planets wobble are going to be due to the gravitational attraction of other planets like Jupiter or Saturn on Jupiter. 41 says dwarf planet Pluto was discovered by perturbations of, well, if you know the order of the planets, so let's say Pluto's way out here. Then before Pluto is what? Neptune and then Uranus. So that's Pluto. Let's say this is Neptune. And let's say this is Uranus with sideways. With the sideways, what do you call it? Ring. So basically, Neptune and Uranus are the two closest planets to Pluto. So basically, these two planets are going to be pulled just a little bit by Pluto, causing them to wobble or perturbate a little bit. And so, the dwarf planet Pluto was basically discovered by the perturbations or the wobbles of Uranus and Neptune. So for number 41, the answer is going to be C. 42 said the ball dropped. A drop ball gained speed because its nature is to come closer to the Earth. The gravitational force acting on it. Its velocity changes because of its inertia. Well, a drop ball basically is in free fall, right? And any object in free fall is acted on by the force of gravity. And so since the force of gravity is acting on that falling ball, it's going to cause it to speed up, and hence, it speeds up as it falls downwards. So 42 is going to be B, a gravitational force acts on it. I think that one's pretty easy. A bowling ball that rolls off the edge of a table, its horizontal component of motion. So have a table here, a bowling ball rolls off of the cliff. The horizontal component, so this horizontal component is basically going to remain constant, right? Because there are no forces in the horizontal direction. The only force is gravity pulling it downwards. And And so the horizontal or the left and right component of motion is going to be constant. So for 43, the answer is going to be A. 44 says, Neil tosses the ball upward at an angle, assuming no air resistance. Which component of velocity changes with time? Well, similar to the bowling ball question, if we throw something at some angle, then we know the horizontal component, or this component here, it's going to be the same throughout the whole motion, right? All those are supposed to be the same length, but the vertical component is what's going to change, right? Because of gravity pulling it downwards. So for 44, it says which component changes with time? That's going to be the vertical component, or the up and down component. So 44 is going to be B. 45 says a projectile is launched upwards at 50 meters per second. Neglecting air resistance, its speed upon returning to its starting point is, well, if you throw something upwards at 50 meters per second, whatever speed you initially throw it upwards with, once it comes back down to that same spot, it's going to be coming downwards with that same velocity. So if I throw a ball up 10 meters per second, it's going to get higher and higher and higher until it stops at the top at 0. And then it's going to come down, speed up, speed up, speed up until it's back in my hand where I threw it up at 10 meters per second. So for 45, the answer is going to be C, 50 meters per second. 46 says a ball rolls off the edge of a table. At the same time, another ball drops vertically from the same table. So we have this table, we have a ball rolling off, and we have a ball, I'll put it right here, it's gonna fall straight down. The question is, the ball to hit the floor first is, well, since they both fall from the same height, then we know both of those balls are actually going to hit the ground at the same time, because the force of gravity only acts on the up and down direction, or the horizontal or the vertical component of the velocity. So this horizontal component can kind of be ignored, because it's still going to be pulled downwards at the same speed because they're both at the same height. And so they're both going to hit the ground at the same time. And so for number 46, the answer is going to be C. 47 says, with no air resistance, a projectile fired at 60 meters, or at 60 degrees, has the same range as if it were fired at what? So let me see if I can draw this out. All right, so let's say basically this bigger angle is 60. This bigger angle here is 60, and this smaller angle is 30. So if you notice, 60 and 30 are, I forget the word for it, but basically they both add up to 90 degrees. So 60 plus 30 equal 90 degrees. So for projectile motion, if you were to launch both of these at the same speed, but at these different angles, they're both going to land at the same point because they both add up to 90 degrees. Similarly, let's say I were to, so instead of 30 and 60, I could do this same thing for let's see, I could do the same thing for these two angles. Well, let's say these two angles are 80 and 20. Actually, say 80 and 10, I mean. So if this smaller angle here is 10 degrees and this bigger angle is 80, because both of those angles add up to 90, they're both going to land at the same spot. And you can do this for whatever combination of angles, so like 30 and 60, or I guess we did 30 and 60 here. It could be 45 and 45. It can be any two angles that add up to 90 degrees. So for number 47, the answer is going to be 30 degrees, or C. 48 says two projectiles fired at equal speeds but different angles. One's fired at 40 degrees and the other at 50 degrees. With no air resistance, the projectile to hit the ground first will be, well, again, this kind of goes back to this, since we can add up 50 and 40, 50 plus 40, equals 90, right? Boom. So since 50 plus 40 equal 90, if you fire both of those at those angles, then they're going to land at the same point because both of the angles add up to 90. So for 48, the answer is going to be C. They both hit at the same time. 49, almost done. So 49 says the tangential velocity of the Earth, of an Earth satellite, is its velocity perpendicular to the surface, parallel to the surface, attributed to satellites moving in any direction. Well, this is the Earth here. This is a satellite going around. The tangential velocity is this here, or for at this point, it's that way, and so on and so on. This velocity is basically parallel with the surface of the Earth. So the answer to number 49 is going to be B. 50 says the moon does not crash into the Earth because, kind of answer the question similar to this. The moon, well, let's say this is the moon and not a satellite. If this were the moon doesn't fall downwards to the Earth because it has some tangential speed this way, right? That causes it to fall around the Earth. So the moon does not crash into the Earth because of B. The moon has a sufficient tangential speed. 51, the speeds of planets around the sun depend on what? Well, they depend on the distance from the sun, right? Just to show you why. So say this were the sun, this is the sun here, and say this is the orbit of a planet, like that. So at this point, its speed's going to be, kind of slow because it's so far away from the sun. But then at this point, when it's really, really close to the sun, it's going to be moving really fast. So basically, the closer, or as this planet gets closer to the sun, it starts to move faster around the sun. And then as it gets further, it slows down. So the speeds of planets about the sun depend on A, their distances from the sun. So the last question is, a projectile that is fired vertically at 5 kilometers per second from the Earth's surface will, so if you're on the surface of the Earth, you fire an object upwards at 5 kilometers per second, well, it's just gonna go really, really, really high and basically fall back down. So the answer to 52 is, it's going to be C. It's going to rise up and fall back to the surface of the Earth. All right, and so that's the whole review. I hope that was helpful, and good luck on your test.